We are going through a little tedious, but so far not very difficult treatment of trying to find an analytic solution for Schrodinger equation of a harmonic oscillator by using the power series method. This is where we had stopped in the last module. Just to do a quick recap, what we are doing is we are proposing the solution of h xi. Please do not forget where h xi comes from or where xi comes from. Xi is simply root over m omega by h cross multiplied by x. The wave function is h, which is a function of omega function of xi multiplied by e to the power minus xi square by 2. Now what we are trying to do is we are trying to find out what this h of xi is. If you remember, for very large values of xi it is a constant, but for all values of xi what is the general expression? To know that, we have expressed this as a power series. H of xi is sum over j equal to 0 to infinity aj xi to the power j, right. And then what we have done is we have written this recursion formula aj plus 2 in terms of aj, and there we have put in j minus v. Hence we have proved that j max is equal to v. You cannot have a j value. What is j value? J is the number of terms in the summation for h of xi. So in the most general form it is an infinite sum. So what we are saying is actually it is a finite sum. You do not need to go beyond the vth term. So which means suppose v equal to 0, then 0th term is enough. 0th term does not mean no term. 0th term means for j equal to 0, what will it be? Xi to the power j will be 0, xi to the power j will be 1, and you will be left with a 0. Okay. Suppose your v equal to 5, that means you have to sum from j equal to 0, 1, 2, 3, 4, 5, that is enough. You do not have to go to j equal to 5,32,097. Okay. That is what is the meaning of j max equal to v. Then we said that now the thing is this recursion formulae connect alternate amplitudes. So depending on whether j is even or odd, all amplitudes for odd or even terms respectively are going to be 0, because you will not be able to access them. Okay. That is what we say in this line, right. So what we have been able to do is we have been able to write instead of 1, 2 separate series, and this time terminated series for the function h of xi. For odd values of v, h of xi is equal to a1 multiplied by xi plus a3 multiplied by xi cube plus a5 multiplied by xi to the power 5, so on and so forth. The last term is av multiplied by xi to the power v. For even values of v, we have h of xi equal to a0 plus a2 multiplied by xi square plus a4 multiplied by xi to the power 4, so on and so forth. Last term once again is av multiplied by xi to the power v. So we have two series, two kinds of wave functions, two kinds of functions, one for odd, one for even. And now, as I said earlier, even when the harmonic oscillator problem was being worked out using quantum mechanics for the first time, the mathematics was already developed for this kind of differential equations, right. That is how science progresses. You do things perhaps without even thinking that there can be an application. You do it because it is there, and then applications often come out eventually. So it was known that this kind of polynomials are actually what are called Hermite polynomials. So I will show you some examples of Hermite polynomials. These are the Hermite polynomials Hv for v equal to 0, 1, 2, 3, 4 and 5. So, you see what you have for v equal to 0, the polynomial is just 1. For these are normalized Hermite polynomials. For v equal to 1, it is 2 xi. For v equal to 2, note you have something in xi to the power 0 and something in xi to the power 2. For v equal to 3, there is no xi to the power 0 term. You have minus 12 xi plus 8 xi cube, that xi square and xi to the power 0 are missing. Similarly, for v equal to 4, you have xi to the power 4, xi to the power 2, xi to the power 0, and it goes on. Okay. So, these are the Hermite polynomials. How do you find the wave function? By multiplying each Hermite polynomial by this common exponent, a common Gaussian function e to the power minus xi square by 2. Using Hermite polynomials has its advantages. In fact, even if you cannot prove it ab initio, what you can do is you can at least verify what I am going to write now. It was known already that these Hermite polynomials have these relations with each other. We have already discussed one kind of recursion relation. Here we have something that is related. This is what it is. I have written it in a little different form than that of the group, that of the book. I have written 2 xi multiplied by hv of xi is the sum of the polynomial after hv plus of in xi plus some constant. Well, this should be 2v, I am sorry, this should not be n, it should be v, 2v multiplied by v minus 1th Hermite polynomial in xi. What does this mean? Let us take anything, let us take xi 3. Multiply xi 3 by xi, what do you get? You get a term in xi to the power 4, you get another term in xi square. Now look at the polynomial after. You have something in xi to the power 4, something in xi square, and you have a constant. Look at the polynomial before, it is 4 xi square minus 2. So, what I am saying is that once you multiply any polynomial by xi, what you get is a linear combination of the polynomial before and polynomial after. It becomes dimensionally consistent as well. Okay. So, this is a very important recursion relation of Hermite polynomials, which obviously also relate the vibrational wave functions, and this is very handy in deriving the selection rule for spectroscopic transition for a harmonic oscillator. Well, the selection rule, as many of us might know, for harmonic oscillator is delta V equal to plus minus 1. You can only jump one step at a time. How that comes, we will not dwell into it further. Whoever is interested can see this recorded module and perhaps the module after this, which is available on YouTube. This is from our NPTEL course on molecular spectroscopy from last semester. Right. Now we can conclude our discussion on quantum harmonic oscillator. We have not really done everything. There are certain things that are left, but we are going to give some of it as a tutorial problem to you, assignment problem to you. But let us summarize what we have learned. First thing we have learned is that when we use quantum mechanics, very naturally vibrational energy of a harmonic oscillator turns out to be quantized. The quantum numbers range from 0 to in principle infinity, and the energy of the Vth level turns out to be V plus half multiplied by h cross omega, which leads to a corollary that a harmonic oscillator can never be at rest. Its vibration energy can never be exactly equal to 0, because as we said several times already, but let me remind you once again, because if it comes to rest, then it means that position is the mean position, so x equal to 0 plus minus 0, and momentum is also 0 plus minus 0. Uncertainty in position, uncertainty in momentum, both are equal to 0. So, uncertainty principle is violated. Uncertainty principle cannot be violated, right. So, it makes sense that a quantum harmonic oscillator can never be at rest. Even at 0 Kelvin, the 0 point energy half h cross omega is there. And in fact, once again perhaps we will give it to you as an assignment. At room temperature for most molecular harmonic oscillators, it is the V equal to 0 level that is only occupied. V equal to 1 level is usually not occupied at room temperature because the energy gap is too large. If you use the simple distribution, then Boltzmann distribution, you will see that for an energy gap of 1000 centimeter inverse, only 8 molecules would reside in V equal to 1 level for 1000 molecules in V equal to 0 level. So, practically at room temperature even V equal to 1 is not occupied, forget about V equal to 2 and 3 and so forth. Okay. So, 0 point energy is a fundamentally important concept for quantum harmonic oscillators. Then we have worked out the general expression for wave functions, and it is beautiful. It is beautiful because it is a product of a constant, a Hermite polynomial and a Gaussian function. The Gaussian factor ensures that no matter how high xi you can go to, the wave function falls off to 0 not too much beyond the potential energy surface. Why it can even go beyond the potential energy surface, remember, is your homework problem, you ought to figure it out, right. And the Hermite polynomials, if you remember, are for V equal to 0 it is just 1, for V equal to 1 it is a first order polynomial. So, first order polynomial means what? Something like xi. So, for xi equal to 0, where is xi equal to 0? For x equal to 0 midpoint. Then what will happen? You will get a node, the wave function will change sign. If you go to V equal to 2, that is a second order polynomial in xi. So, equate that to 0, you will get 2 roots, and these are the 2 roots where the wave function will not only become 0, but change sign. Please remember, a node is a point or later on a plane or surface or something where wave function changes sign. It goes through 0, but it has to change sign. For example, if you go here at x equal to infinity or xi equal to infinity, there also the wave function is equal to 0, but xi equal to infinity or x equal to infinity is not a nodal point because the wave function becomes 0 asymptotically, it does not change sign. So, as you go higher up the energy ladder, you get more and more and more nodes. That leads to this rule of thumb that more the number of nodes, higher is the energy associated with the wave function. Okay. And the nodes here come from the Hermite polynomial being equated to 0. Okay. Whatever is the order of the polynomial will be equal to the number of nodes. Okay. That is why we get more and more nodes as we go higher up. Then we have learned that recursion relation is there among connecting these wave functions. So, just multiply a wave function by xi, you will be able to get a linear combination of the wave function before and wave function after. So, that is all for simple harmonic oscillator. This, as we said earlier, has very profound application in vibrational spectroscopy. Next we move on to rigid rotor, which also has profound application in rotational spectroscopy, but also one more reason why we study it is that the methods that we develop there are going to come handy when we talk about the first molecule the first atom, hydrogen atom. Remember, this course is on quantum chemistry of atoms and molecules. We have already learned the quantum chemistry of vibrating molecules. Now we will learn the quantum chemistry of rotating molecules, and that will enable us to get into a hydrogen atom in which Schrodinger equation is exactly solvable. Okay. That is what we will take up in the next few modules.